Okay, so I thought it'd be helpful for us to take a look at a little bit different circuit and practice one more time by way of example of circuit analysis. And here we have a circuit that looks a little bit complex with some diagonal things going on and multiple resistors, and hopefully we can recognize right away that there are some series and some parallel combinations. And when we do analysis on this circuit, we're going to try to come up with two main objectives. We want to find the total equivalent resistance of this circuit, and we want to find the total current through this circuit. Now, to do analysis here, it's actually pretty easy. We can condense this circuit down to an equivalent circuit. That looks like it says RB, but that is R8. And we can start on the right end of the circuit. And one of the first things that we should notice is that these two resistors are in series with each other. Now remember, it doesn't matter what the geometric configuration of the circuit is. It's how it's connected electrically. And we'll use that concept here during this example. So we know that resistors in series, so the equivalent resistance for resistors in series, they just add proportionally. And we know that resistors in parallel add inversely. So we'll use those two concepts as well. Okay, so if we look at these two resistors that are in series, we can actually draw this as one equivalent resistor. So we'll take him out of the circuit, and instead of a 3 ohm resistor, our 3 ohm resistor plus our 9 ohm resistor looks just like one 12 ohm resistor. So we've got an equivalent circuit that eliminated one of the resistors from the diagram. So if we take that concept a little bit further and we look here, we have a 12 ohm resistor and a 12 ohm resistor in parallel with each other. So the equivalent resistance of two 12 ohm resistors is 1 over 12 plus 1 over 12, which is 2 over 12. And if we invert that, looks like we've got one 6 ohm resistor. So we can eliminate this guy from the circuit, and he now looks like a 6 ohm resistor. Okay, so moving along, we've got the same concept here and here. We've got two resistors in series, okay? So we can add their resistances together to find an equivalent resistance. 6 ohms and 6 ohms now looks like a single 12 ohm resistor. So now we come to this guy. What are we doing about this guy? He's diagonally connected between this node and this node. Well, does that really matter? If we don't have to change the circuit at all electrically, but if we just take this node and rotate it a little bit, it's still connected here and it's still connected here, which electrically is the same spot in the circuit. And what we've really got is two 12 ohm resistors in parallel with each other. So we can eliminate this guy from the diagram, and now he just looks like a single 6 ohm resistor. So now that we've got this equivalent circuit, so let me kind of update this circuit. We've got R1 right there, which is 3 ohms, and we've got R2, which is 4 ohms, and R3, which is 2 ohms. And now we've got our other parallel resistor, which is 6 ohms. This circuit is exactly electrically equivalent in terms of total resistance to this circuit. So now we can look at this, and we've got a 4 ohm and a 2 ohm resistor in series, which just look like a 6 ohm resistor. So we can further condense the circuit. We've got a 6 ohm resistor and a 6 ohm resistor in parallel with each other, and that is going to look like a single 3 ohm resistor. Now we're down to a 3 ohm resistor and a 3 ohm resistor in series with each other. We can eliminate that guy, and he looks just like a single 6 ohm resistor. So our total equivalent resistance of this circuit is 6 ohms. Now we go to the total current through the circuit. Remember from Ohm's law, V equals IR. So we're trying to find the current So it's going to be our total voltage over our total resistance. And we see here V1 is 6 volts. 6 volts divided by 6 ohms is 1 amp. So we have 1 amp leaving the battery, and it goes various ways throughout the circuit, and now we have 1 amp returning to the battery by Kirchhoff's current law.